So moving coil galvanometer डिपेंड कर रहा है फ्लेमिंग्स के रूल के ऊपर, उसकी डायरेक्शन फ्लेमिंग के रूल पे डिपेंड कर रही है। क्या क्या चीजें होती हैं इसमें, वो सारे का सारा मैं भी आपके साथ डिस्कस कर रहा हूँ। तो प्लीज उसे अच्छे से नोट करो और उसके बाद डिस्कस करना मेरे साथ।
and the stick turns.
ऑडिबल है सबको?
Yes, sir.
Yes, sir.
जी।
Pass current through a galvanometer and the stick turns. If you increase the amount of current passing through the galvanometer, the stick turns even more, showing more current, indicating more current. But how does passing current through something make a stick turn? Well, that's exactly what we want to find out in this video. The principle behind this
अब यहाँ से आपका मेन स्टार्ट होगा कि कौन सा प्रिंसिपल है इसके बिहाइंड और किस तरह से डायरेक्शन, किस तरह से फोर्स लगेगी कॉइल के ऊपर और क्या क्या होगा।
moving coil galvanometer is if you take a coil and pass current through it, then it will start producing a magnetic field. And this field resembles that of a bar magnet.
यहाँ पे आप ग्रेड 10 में आपने पढ़ा था, जब भी किसी कॉइल में से करंट फ्लो करता है, अगर करंट की डायरेक्शन एंटी क्लॉकवाइज है तो वहां पे नॉर्थ पोलैरिटी होती है, और अगर क्लॉकवाइज डायरेक्शन है देन पोलैरिटी साउथ होगी। बाय द सेम मैनर अगर हम बार मैग्नेट को देखें, बार मैग्नेट में एक साइड नॉर्थ पोलैरिटी, दूसरी साइड साउथ पोलैरिटी। तो जैसे इस कॉइल में से करंट फ्लो करता है, एक अगर यहाँ पे आप देखो तो कौन सी डायरेक्शन है इसकी नीतीश?
सर आउटसाइड द पोल आ रही है।
हाँ, तो फिर एंटी क्लॉकवाइज हो गया है ना।
हाँ जी।
एंटी क्लॉकवाइज है तो नॉर्थ पोलैरिटी अपवर्ड बनेगी, साउथ पोलैरिटी डाउनवर्ड। अगर नॉर्थ पोलैरिटी अपवर्ड है, देखो यहाँ से मैग्नेटिक फील्ड लाइंस नॉर्थ से बाहर निकल रही है और साउथ से एंटर कर रही है। ठीक है।
And so we can pretty much assume that this current carrying coil behaves like a bar magnet. Now keep this between the two poles of an actual magnet. You can imagine this is a part of a horseshoe, large horseshoe magnet. Then what will happen? Well, if you imagine this current carrying coil to be a bar magnet, it's not really, okay, but you're imagining it this way. Then you can see that the north gets attracted by the south pole towards the right. The south gets attracted by the north pole towards the left, and therefore the coil tends to turn. And there you have it. Current is making the coil turn. Now all you have to do is attach a stick to it as an indicator, put some markers, and we see as you pass current through it, that torque is going to make this thing turn, 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 turn. And this is where there's a problem. This turning will not stop. You see, as long as there's a current over here, the torque exists, and the torque will keep on making it turn. And so this is a problem for us. You see, what we would want is that turning to stop at some point. We would ideally want that for small currents, it'll only turn by a small angle. And for large currents, they should turn by a large angle. That's what a galvanometer does, right? But that's a problem over here. That's not happening. For any current you put, this thing will keep on turning until it gets stuck somewhere. So that's problem number one for us. And if we get rid of that current, if we stop the current, it'll stop behaving like the magnet. So the torque disappears and nothing happens. Now it just stays there. It doesn't come back. So this is a terrible galvanometer. This is problem number two. It doesn't spring back. So the question now is, what do we do? How do we improve this? So can you think of how do we solve this? There are two problems. Problem number one is, let me bring this back. First problem is, we would want the pointer, the coil to stop turning at a particular point, depending upon how much current we have. For more current, we would want it to turn more before stopping. That's problem one. And the second problem is, when you get rid of the current, we would want that thing to snap back. How do we ensure that? Can you pause and think a little bit about this? All right, have you given this a thought? Well, here's the solution. We want this to snap back, right? What object comes to your mind when it comes to that? Springs. When you stretch a spring, it tends to snap back. But the springs like these are useful for linear motion. Here, we would want it to snap back, turning motion. So we would want not normal springs, but we would want to use coil springs. So these are the two coil springs that we are attaching. Two, because we want this thing to remain stable. These ends are fixed, and the other end is attached to the coil. Now, again, if we run a current, we now know this acts like a magnet, and as a result, there is a torque acting on it, and this thing tends to turn this way. But now as this turns, these springs, they get coiled. Look at the springs carefully. And as a result, the springs tend to uncoil themselves. In other words, they put a torque in the opposite direction. We can call this the counter torque. And at one particular point, the torque due to the magnetic field and the counter torque balances out and the pointer stays stationary. So we've solved our first problem. Now think about what would happen if we were to increase the strength of this current. Now the coil will act like a stronger bar magnet, and as a result, the forces between these pole pieces of magnet increases. In other words, the torque, the turning force, the torque increases, and so the coil now turns more. Again, eventually until the counter torque equals the torque of the magnetic field. So for more currents, we get more deflection, exactly what we wanted. And of course, if we get rid of the current, the torque due to the magnetic field disappears, the counter torque brings the coil back, and the coil comes back to 0. So yay, we have our galvanometer. We just now have to put this together in a box and construct it, and we can start selling it, right? Well, not quite. There's one last challenge that we need to solve for. We need to make sure that this is a linear device. What do I mean by that? See, now we know for more currents, we get more deflection. But we need to make sure that the amount of deflection is proportional to the current. That means if we were to double the current, we need to make sure that the deflection doubles. Only then we will have a linear galvanometer. Only then this measuring system will work. So, to put in other words, if you pass current through it and say the coil comes to equilibrium in this position, let's say by making an angle theta, let's imagine that it turned by an angle. Let's not use theta. I will need theta for something else, we'll see. By turning an angle phi, mathematically, we need to make sure that the angle phi is proportional to current. Does that make sense? Otherwise, we don't have a good galvanometer. So that if my current were to double now, it should show 10. That means the deflection should become twice. This angle should become twice. So how do we ensure this is the question. And so how do we ensure this? Well, we can do that mathematically. We can start by building equations. But again, how do I start? Where do I start? Well, I know we're talking about turnings, and turnings is about torques. We already have torques over here. And we know that at equilibrium, the torque due to the magnetic field exactly equals the counter torque in magnitude. So we can start over there. So we can say at equilibrium, the counter torque, I'll just call that as the TC, that's the counter torque, must be exactly equal to the torque due to the magnetic field. The torque due to the magnetic field. I'll use B for magnetic field. All right, so what does the counter torque depend on? Well, the counter torque depends upon how much the spring twists. More the twisting, more is the torque. And in these springs, they are proportional to it. So we can say the torque is proportional to the angle of twist, which is phi. All right, or we can also write it is equal to some constant C, which that constant will completely depend upon the spring, some constant C times phi. So this is our counter torque. And that at equilibrium should equal to, in magnitude, they're in opposite direction of course, should equal to the torque due to the magnetic field. Now comes the question, what is the torque due to the magnetic field equal to? This is something that we have talked about in previous videos, so I'll not try and derive this over here. So I would like to pause the video and see if you can remember this. What does the torque due to the magnetic field depend on? The movement of this coil is the magnetic field between the assumed, and hopefully that makes sense, because as the angle becomes smaller and smaller, the torque becomes smaller and smaller. Think about it, when the angle becomes 0, your bar magnet will be completely horizontal and there'll be no more torque acting on it. All right, So what is that equal to? Well, what is M equal to? The magnetic moment of this particular, this coil, well, that is equal to, again, something we derived before, so I'm not going to try and derive this over here. It's going to be equal to the number of turns of the coil times the strength of the current, how much current is passing through the coil, times the area. So this is our magnetic moment times the magnetic field times sine theta. And now let's see. Is our phi, so here's our C times phi, is our phi proportional to current? So we just have to think about whether the rest of the stuff are constants. Well, this is a constant, N is a constant, I for a given current, I is a constant, A does not change, B is a constant, but theta is not a constant. As the thing turns, theta keeps changing. So what we are getting is
इसका डायग्राम ड्रॉ करिए सबसे पहले। मूविंग कॉइल गैल्वेनोमीटर में ये हमारे पास एक बॉक्स होता है, लेवल स्क्रू LS। अभी आपने देखे दो मैग्नेट पोल, नॉर्थ पोल एंड साउथ पोल, उसके बीच में यूनिफॉर्म मैग्नेटिक फील्ड, एक टोरिजिनल हेड T, जिससे एक ब्रॉन्ज वायर जाएगी कॉइल के ऊपर, कॉइल है PQRS, वहां से हेयर स्प्रिंग टोरिजिनल स्टैंड के ऊपर। इसे ड्रॉ करो सबसे पहले। ड्रॉ हो गया इतना?
सर एक से निकलना है लास्ट। डन सर।
एक मिरर होगा M, और जो इलेक्ट्रिक करंट हम अप्लाई करेंगे बाहर से, उसकी EMF। जैसे हम की इंसर्ट करेंगे, करंट फ्लो होना स्टार्ट हो गया, देखो सारा। और टॉर्क एक एग्जिस्टेंस में आएगी, अप आउटवर्ड और इनवर्ड डायरेक्शन। तो ये सारी की सारी वर्किंग है, इसे प्लीज नोट कर लीजिए। दिस इज ऑल अबाउट मूविंग कॉइल गैल्वेनोमीटर। मैं इसके नोट्स भी आपको सेंड करूंगा, और कल आपका सिर्फ मूविंग कॉइल गैल्वेनोमीटर का ही टेस्ट होगा। सिर्फ एक ही क्वेश्चन, मूविंग कॉइल गैल्वेनोमीटर। जल्दी से नोट करिए प्लीज।